We all experience gravity every day. It's a force so familiar that we often take it for granted. From the moment we wake up and place our feet on the floor to the time we lie down at night, gravity is constantly at work. It's the force that keeps our feet on the ground, allowing us to walk, run and jump. Whether we're strolling through a park or hiking up a mountain, gravity is there anchoring us to the earth. It makes objects fall when we drop them. From a simple pen slipping from our fingers to a majestic apple falling from a tree, gravity ensures that what goes up must come down. Gravity is a fundamental force in the universe. It's not just a force we feel on Earth, it's a cosmic phenomenon that governs the motion of celestial bodies. It affects everything, from the smallest particles to the largest galaxies. Even in the vast emptiness of space, gravity's influence is ever-present, guiding the dance of the cosmos. Without gravity, our world would be unrecognizable. Imagine a place where objects float freely, where there is no up or down. This is the reality astronauts face in space. We wouldn't have planets, stars, or even galaxies. Gravity is the architect of the universe, shaping the formation of stars and the orbits of planets. Gravity is the glue that holds the cosmos together. It binds galaxies, clusters of stars, and even entire galaxy clusters, creating the intricate web of the universe. It shapes the universe as we know it. From the bending of light around massive objects to the formation of black holes, gravity's effects are profound and far-reaching. In this exploration, we will journey to understand this fundamental force. We will delve into the mysteries of gravity, uncovering its secrets and marveling at its power. We will see how gravity shapes planets, stars, and galaxies. From the orbits of planets around their stars to the spiraling arms of galaxies, gravity's influence is everywhere. We will even venture into the mysteries of black holes. These enigmatic objects, with their immense gravitational pull, challenge our understanding of physics and the nature of the universe. Join me as we unravel the secrets of gravity, the force that governs the cosmos. Together, we will explore its wonders and appreciate the role it plays in shaping the universe we call home. Sir Isaac Newton first described gravity as a force of attraction between any two objects with mass. His groundbreaking work in the 17th century laid the foundation for classical mechanics. Newton's law of universal gravitation was revolutionary, explaining how every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. The more massive an object, the stronger its gravitational pull. This principle helps us understand why planets orbit stars and why moons orbit planets. The gravitational force is what keeps the celestial bodies in their respective orbits, maintaining the delicate balance of our solar system. This force is what makes an apple fall from a tree and the moon orbit the Earth. Newton's insight came from observing an apple fall, leading him to ponder the forces at play. This simple observation led to a profound understanding of the natural world, connecting the motion of objects on Earth to the motion of celestial bodies. Albert Einstein revolutionized our understanding of gravity in the early 20th century. His theory of general relativity, published in 1915, provided a new framework for understanding gravity, one that went beyond Newton's laws. Einstein's work was driven by the need to reconcile the laws of mechanics with the laws of electromagnetism. He proposed that gravity is not a force, but a curvature in the fabric of space-time, caused by mass and energy. This was a radical departure from the Newtonian view. According to Einstein, massive objects like stars and planets create dents or curves in space-time, and other objects move along these curves, which we perceive as gravitational attraction. Imagine a bowling ball placed on a trampoline. It creates a dip. Smaller objects placed on the trampoline will roll towards the bowling ball, not because of a direct force, but because of the curvature created by the bowling ball. This analogy helps us visualize how massive objects warp space-time. Similarly, massive objects warp space-time. The more massive the object, the greater the curvature it creates. This warping of space-time affects the motion of other objects, guiding them along curved paths. Einstein's theory, called general relativity, explained some phenomena that Newton's theory couldn't. For instance, it provided a more accurate description of the orbit of Mercury, which Newton's laws couldn't fully explain. General relativity also predicted the existence of black holes, regions of space-time where gravity is so strong that not even light can escape. For example, it explained the bending of light around massive objects, a phenomenon called gravitational lensing. This effect has been observed in numerous astronomical events, providing strong evidence for Einstein's theory. Gravitational lensing allows us to see distant galaxies and stars that would otherwise be hidden behind massive objects, offering a window into the far reaches of the universe. In our solar system, gravity is the choreographer of a delicate dance of planets. The Sun, being the most massive object, exerts the strongest gravitational pull. This pull keeps all the planets, including Earth, in orbit around it. The planets also exert their own gravitational forces, albeit much weaker than the Sun's. These forces cause slight perturbations in each other's orbits. Jupiter, the largest planet, has a particularly noticeable effect on the orbits of other planets and asteroids. Gravity plays a crucial role in the life cycle of stars. Stars are born in giant clouds of gas and dust called nebulae. When a region within a nebula becomes dense enough, gravity pulls the gas and dust together. As more and more material collapses, the center of the cloud heats up under immense pressure. Eventually, the temperature and pressure becomes so high that nuclear fusion ignites. This process releases an enormous amount of energy, and a star is born. Gravity continues to play a vital role throughout a star's life. The outward pressure from nuclear fusion balances the inward pull of gravity, keeping the star stable. Section 5. Galaxies, islands in the cosmic sea. Galaxies are vast collections of stars, gas, dust, and dark matter held together by gravity. Our own galaxy, the Milky Way, contains hundreds of billions of stars. Gravity acts over vast distances, binding these stars together. Galaxies come in various shapes and sizes, including spiral, elliptical, and irregular galaxies. The shape and structure of a galaxy are influenced by its rotation, the distribution of its mass, and the gravitational interactions with other galaxies. Section 6. The Milky Way and our galactic neighborhood. The Milky Way is a barred spiral galaxy, a majestic swirl of stars, gas, and dust. Our solar system resides in one of its spiral arms, about 2/3 of the way out from the center. We are constantly moving through space, orbiting the galactic center. The Milky Way is part of a larger cosmic structure called the Local Group, a collection of about 50 nearby galaxies. The Andromeda Galaxy, our nearest major galactic neighbor, is also a member of the Local Group. Section 7. Black holes, gravity's ultimate triumph. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse at the end of their lives. Imagine the Earth squeezed into a sphere the size of a marble. That's the kind of density we're talking about. Black holes are invisible to telescopes that detect light, but their presence can be inferred by their gravitational effects on nearby stars and gas. Astronomers have discovered evidence of black holes at the centers of most galaxies, including our own Milky Way. Section 8. Warping time and space. One of the most mind-bending predictions of Einstein's general relativity is that gravity affects time. Time slows down in stronger gravitational fields. This phenomenon, known as gravitational time dilation, has been experimentally verified. Gravity also warps space, as we discussed earlier. This warping of space-time is what causes the bending of light around massive objects, a phenomenon known as gravitational lensing. Gravitational lensing can act as a cosmic magnifying glass, allowing us to see distant objects that would otherwise be too faint to observe. Section 9. Unraveling the mysteries of dark matter and dark energy. While we have made significant strides in understanding gravity, some cosmic mysteries remain. Two of the most profound are dark matter and dark energy. These enigmatic entities make up the vast majority of the universe's mass and energy budget. Dark matter doesn't interact with light, making it invisible to telescopes. However, its gravitational effects are evident in the rotation of galaxies and the large-scale structure of the universe. Dark energy, on the other hand, is a mysterious force that is causing the expansion of the universe to accelerate. Section 10. Gravity's grand design. From the fall of an apple, a seemingly simple event that sparked the curiosity of Sir Isaac Newton centuries ago, to the majestic dance of galaxies, gravity shapes the cosmos on every scale. It is the invisible force that binds the universe together, orchestrating the movements of celestial bodies in a grand cosmic ballet. It governs the motion of planets, stars, and galaxies, ensuring that they follow precise paths through the vast expanse of space. Without gravity, the universe as we know it would be a chaotic and unrecognizable place. Gravity sculpts the very fabric of space-time, creating the gentle curves and warps that influence the flow of time and the path of light. It is the reason why light bends around massive objects and why time itself can slow down in the presence of immense gravitational fields. While we have come a long way in our understanding of gravity, many questions remain. Scientists and researchers around the world continue to delve into the mysteries of this fundamental force, seeking to uncover its deepest secrets. The nature of dark matter and dark energy, which together make up most of the universe's mass-energy content, remains one of the biggest enigmas in modern astrophysics. These unseen components exert gravitational forces, yet their true nature eludes us. The behavior of gravity at extreme scales, such as near black holes or during the collision of neutron stars, challenges our current understanding and pushes the boundaries of theoretical physics. The search for a unified theory of gravity and quantum mechanics, a theory that can seamlessly explain the workings of the cosmos from the smallest particles to the largest structures, is one of the most ambitious quests in science. As we continue to explore the universe, gravity will undoubtedly continue to surprise and amaze us. It will reveal the secrets of the cosmos and our place within it, guiding us on our journey to understand the grand design of the universe.